All right, section 4.2. So we started section 4.1, or we did section 4.1 in the last couple class periods. And we talked about historical numeration systems. Which systems did we use? Chinese, Roman, and Egyptian. Those were the three. Good job. Now, the nice thing about all those systems was that they each had either just a repetition symbols, or the symbols weren't quite so difficult to write. The Egyptians, they weren't so nice to write. But the conversions were all pretty clean, right? I mean, to convert back and forth, probably the most difficult one, really, to be honest, is the Roman one, and we're a little bit more familiar with it, because this subtraction feature thing is a little bit unusual. Everything else was either like we just grouped a couple things together, or we just wrote a bunch of symbols down. Okay, things are going to change a little bit today. The first system that we're going to look at is the Babylonian numeration system. The cool thing is they only have two symbols, so we're going to start there, okay? So two symbols. One of them has the value 1, and the second one has the value 10. The value for the system 1 is an upside-down triangle, and if you draw it and don't fill it in, that is, if you draw it like this, I'm okay. Okay, so if you don't want to take the time to fill it in, don't. The 10 looks kind of like a sideways triangle or like a boomerang shape, or a little bit like a less than sign. And if you really just want to draw it as a less than sign so that it doesn't sort of start to look like the other symbol for me, I'm okay with that too. All right, so these are the actual ways that the symbols look, at least sort of. And then these are sort of the options, if you'd like to, that I'm all right with you drawing. Okay, so here's where things get a little funny. Here's the first one. So this is a repeated symbol. They use repeated symbols. Okay, we've seen repeated symbols used before. So if we wanted the number 20, we'd use 2 10s, right? No problem. And they do that for each value less than 60. Okay, so once they get past the number 60, they do something different. When they get past the number 60, they use a positional-based 60 system. Well, we use a positional system as well. Ours is a base 10 system. So we have the ones place, the tens place, the hundreds place, because we don't have a separate symbol, per se, for the number 11, right? We use the symbols that we had before. Okay, same thing for them. And then they do not have a number 0 in their system, and we're going to see how that can cause problems. Okay, I think we're about done with writing. Is everybody okay for me to switch the slide? All right. These are our first two problems. Okay, so go ahead and write them down. They're beautiful when I have time to draw them, not in the middle of class, right? They actually look pretty good. So you see some triangles, you see some of those less than boomerang kind of shaped signs. So jot down the right number in the right spots, and then I'm going to show you how their system works. It is kind of like cuneiform, yeah. All right, so let me talk a little bit about our base system just briefly so that you can kind of have a feel for how it works in their base system. In our base system, we have some different place values, right? We have the ones place, and then we have the tens place, and then we go up from here, and it's actually 10 squared, which is actually another way of writing the number 100, right? And then we have 10 cubed and 10 to the fourth. Powers of 10. It's all powers of 10 because it's a base 10 system. Agree? All right. So in their system, they have base 60 system, but they still have this positional idea. That is, there's a placeholder for a value 1, and there's a placeholder for their next value, which happens to be 60s. There's going to be a placeholder for 60 squared, right? Because we had 100, which was our 10 squared. It's going to all be powers of 60. Now, we have to decide where place values start and stop, and there is a uniform way of doing that. So let's just go through this one right here, and I want you to tell me what each of the symbols are worth. So what's the first symbol? 10, and then 10, and then 1, and then 10, 10, 1, 1. Okay, so you notice we've got some 10s and some 1s in there. I mean, they're all 10s and 1s, right? Okay, so remember with the Romans, the bigger value was always before the smaller value, except when they had the weird subtraction thing going on. And remember with the Babylonians, it was like, not Babylonians, Egyptians, it was like that too. The bigger symbol was always before the smaller symbol. Same thing here. If you see a bigger symbol and then you see a smaller symbol, that's perfectly fine. The problem is that when you see a smaller symbol before a bigger symbol, something else is happening. So that happens exactly once in this number. It's right here, right? To the left-hand side of that, I have the numeral 1, and to the right-hand side of that, I have their numeral that's for 10. So when we see a smaller number in front of a bigger number, what happened in their system is we changed place value. So this one right here is their first place value. Okay. And this one right here is their second place value.
So we're reading it from right to left.
Well, we're reading it just like we do from our system. This is the ones place, just like for us. And then it'll be the 60s place on the left-hand side of it, just like for us, that the bigger place value is to the left. So that part actually matches up with what we do pretty well. What's different is that there's base 60 instead of it being base 10. So let us write down for the moment just what value these each are. So before the line that's vertical in pink, we've got a couple of symbols, 3 symbols. What number would that be? 21, because I have 2 10s and a 1, right? So this is 21. And what number do I have after my pink vertical line? That's 22. Okay, so I want you to imagine, and this is just to help you get a grip on how to think about their system, not because they would have thought about it this way, but to help you kind of think about their system. I want you to think about it in terms of money. Okay? So in our system, we have a lot of different kinds of bills. But if we had a $1 bill, a $10 bill, and a $100 bill, and that's all we had, okay, so 1s, 10s, and 100s. Are you everybody good with that? Then you wouldn't want to carry around 15 $1 bills in your wallet. You would prefer to take 10 of those $1 bills and to turn them into a $10 bill, right? Less to carry around. It's sort of the natural thing we do. In fact, it's what happens when you go to the cash register and you check out. Naturally, their inclination, unless they don't have the bills, is to give you the fewest number of bills possible. Agreed? That's our goal here too. We want the fewest number of these items possible. Okay? So what you're seeing here is you're seeing that we have kind of like in our system we have 1s and 10s and 100s. They have $1 bills. Okay, again, this isn't the right language, but it's a helpful thing to think about. And then they have $60 bills. Okay? So if you have 21 $60 bills, the question is, how much would that be worth? Well, think about with us. If we had 13 $10 bills, how would you decide how much that was worth? You multiply. 13 times 10, right? You do the same thing for them. If they have 21 of these things that are in the 60s place, if they have 21 $60 bills, we multiply to find out how much that's worth. Are we all good? Multiply. So we're going to take the 21 and we're going to multiply by 6. That's not happened before. That's an iPad thing. That was not an Apple TV thing. All right, so we're going to multiply 21 times 60, and then we're going to multiply technically 22 times 1. I realize that's just 22, but just for the sake of seeing it, I'm going to write it down. So you take the number that's in the place value times the value of that place, plus the number that's in the next place value times the value of that place. And if you multiply, what do you get? 1260 on the first one, and 22 on the second one, for a total of what? 1282. Okay? Let's try it again. So we're looking, we can start from left to right, we can start from right to left. It really doesn't matter. But we're looking for the places where I see a smaller digit in front of a larger digit. And where I do that, I'm going to draw a line to cut in half my place values. Okay? So I've got these 4 symbols, which are all tens. And then I've got these 3 symbols, which are ones. And then I've got these 2 symbols, which are tens. And that right there was a place value switch, right? Because I went from ones to tens. So I'm going to draw a place value in here. Let me use that same pink I used before. Right here. Oh, I'm sorry. And then I did it in the wrong spot. Right here. Right? Ones and then tens. Okay. I have 2 tens here, and then I have a 1, and then I have a 10. So I need another place value change right there. And then again, I have a 10 at the end here, and then a 1, and I'm fine with that, right? Okay. So we have 3 place values here in this number. Agreed? Okay. So looking at these place values, I have the ones place, I have the 60s place, and then what happens? 60 squared. And what is 60 squared? What do you have? 3,600. That one's correct, yeah. 60 times 60 will be 3,600. It's all good? Okay, now we're going to go back, I'll use a different color, and we're going to count how many's in each of the values. So the first one, in the 60 squares, the 3,600 place, the stuff before the first pink line, how much is here? 43. So I'll just write it underneath here. There's 43 of these, because I'm out of space above. How about in the middle, between the 2 pink lines? 21, right? Mm-hmm. And then at the end, after the last pink line, 11. So what operation am I going to use to find out how to make this work? Multiplication. I'm going to multiply the place value times what's in that place value. I'm going to multiply my blue numbers by my yellow numbers, as the ones I've written down now. So we're going to do this over here to the side. We're going to take 43 times what? 3,600. Good. And then we're going to take what? 21 times 60, or 60 times 21, right? Plus what? Technically 11 times 1, or 11, right? We're going to add that all together. So do your multiplication, do your addition. Does anybody have a calculator? I don't see any calculators out. Oh, you got one. Thank you, Brittany. What do you have?
156,071.
That's what I have too. Good. It's always good when they match. All right. So if we are going from their number system, the weird symbols, into our number system, the operation we use is multiplication. Write that down.
Okay.
Okay, that is important because we're about to go the other direction. What do you think is going to happen when we go from our system into theirs?
Division.
Division. And probably 4 of you will do it wrong on the test. You'll switch where the multiplication and the division go. Make sure you're not one of the 4. Okay, write it down. Okay, the directions you go are important. Otherwise, your answers are obviously not going to be right. I'd rather nobody just do that for the sake of argument here. I'm not encouraging 4 people to do that. Okay, so we're going to take our numbers and turn it into theirs now, and the operation we're going to use to do that is division. I'm going to show you an interesting scaffolding or sort of a structure for doing the division. It's going to look a little like long division and a little not like long division. Okay, so we're going to give it a shot. What you have to first recognize to do what I'm about to do with any base change, which is what we're doing, we're changing from base 60 into base 10, is you have to know what the place values are in that base system. So you guys know that they had a ones place, and they had a 60s place, and they had 3,600, because it was 60 squared.
That doesn't look like 306,000.
No, it's not. It's 3,600. This is 1's place, the 60's place, the 3600's place.
Well, number 3 doesn't look like 3600 to me.
I agree, it's not 3600, Leah, but we're just writing down the different numbers right now in their place values. So we'll fix it in a minute, I promise, okay? What would come next if we had a number that we needed that was bigger than this?
60 cubed.
60 cubed. So, Brittany, what's 60 cubed? What did it give you?
4.66.
I think you got too many. Try again. Tell it to do 60 cubed one more time. 60 cubed. No, not 3600 cubed. Although that would still be part of base 60, it'd be much further down the line. What do you get?
Hey, 216,000.
That's right. You're both right. 216,000. That's 60 cubed. Okay? So, what you want to notice is kind of what Leah noticed already on number 1. Number 1 is already smaller than 3,600, right? So I don't need the 216,000. I don't need the 3,600. The first number I'm going to start dividing by is 60 because it's the biggest number in that list of numbers that will actually go into what I'm working with. So we're going to take the 60 and we're to divide the 3280 by 60. But this is right here what normal division would look like. Agreed? I mean, this is what you would write down. I want you to write a bar underneath the 60 and then a bar on top and over to the other side of the 80, the 3280. Okay, this looks terrible. I'm going to try one more time on the whole thing. That's a little bit better. All right. So the division works the same way, but here's what I want to encourage you to do. Grab a calculator. I want you to take 3280 and divide by 60, and what I want to know is the whole number part of the answer. I know it's going to have some decimals after it. I don't care about the decimals. Ignore them for the time being. I just want to know the whole number part when you do the division. 54. Okay. And then what we do when we do long division is you take that number that you just got and you multiply it by the 60 that you were dividing by. Okay? So I want you to take 54 times 60. What do you have? 3240. And you write it down, and then what do you do with it? You subtract. So what is 3280 minus 3240? 40. Now, the next step's going to look a little bit funny for what we're doing, but I'm going to do it for consistency's sake so it will match up with what I want to do with this particular scaffolding later. I'm going to then divide by 1. Okay? I know. It's very exciting to divide by 1. Because how many times will 40 go into 1? 40 times? Or will 1 go into 40? I said it wrong. 1 goes into 40 times. All right, so I've got a 54. I've got a 40. So what I really have in their system is equivalently I have 54 here and I have 40 here. Okay? This is the 1's place. This is the 60's place. Am I done? What is wrong? It's not in Babylonian. Right now we've got our numbers written into those placeholders and we need to write it in Babylonian. So how do I write 54? 5 triangles?
5 boomerangs.
Ah, you're right. 5 boomerangs or 5 less thans. And then what? 4 triangles. Stack them, don't stack them. It really doesn't make any difference. Okay, so if you choose not to stack them, just write them left to right, all on one line. That's great too. No big deal. How do I write the number 40 then? Yep, 4 of the less than signs. And this right here would be my solution. 50 and then 40 within the base 60 system would be the number 3280. All good? Okay. Let's try the next one. The next one, I need to divide by something bigger than 60 to start with. How come? Because it's bigger than 3,600. So I'm going to divide by the biggest thing in this list of numbers that will go into the number I have, and 3,600 would be that number, right? So my division is actually going to start with 3,600 this time. All right, so how many times will 3,600 go into 43,205? What's your calculator give you when you divide the whole number part? 12. Thank you. And then what's 12 times 3,600? 43,200. That's nearly the number I've already started with, huh? All right, so if I subtract, what's left? 5. Now, I understand that 60 is not going to go into this, but I'm going to write it down over here. And again, this is partly because of what we're going to be doing with the scaffolding later. I don't want to leave any of the place values out. How many times will 60 go into 5? 0, it won't. So I'm going to put a 0 over here. 0 times 60 is 0. I know it looks funny, and I promise it will make sense later when we get there. That's going to give you a 5. And then I'm going to put the 1 over here. And how many times will 1 go into 5? 5 times. Okay. So after I've done this, the nice kind of thing about this is that you can see from the scaffolding the answer. There's 12 $3,600 bills. There are 0 $60 bills, and there are 5 ones. Everybody see that okay? How do I write the number 12? In Babylonian, how do I write the number 12?
1 boomerang and 2 triangles.
1 boomerang, 2 triangles. That's what you're saying too, Austin, right? Perfect. 1 boomerang, 2 triangles. And then there is no number 0. I told you we were going to run into a problem with that. We're about to see it. So I don't write anything when I get a 0. The next thing it says then is that I have the number 5. How do I write 5?
That's 5 triangles.
5 triangles. Okay. So if we write our 5 triangles stacked, we at least don't get some of the problems. Okay? If you choose not to write your triangles stacked, it look like that. And that's perfectly acceptable too. All right, so somebody tell me the problem. It looks like everything's in the 60s place, doesn't it? And this number would be 17. And I don't know about you, but if I loaned somebody $43,205 and I wrote down that number in Babylonian, I would want to make sure that they didn't really think they owed me 17. Right? I mean, this isn't good.
I'm not drawing line between them.
Okay, so there's some questions like, what could we do? One of the options would be that we would have sort of like a little bit of a space between them. But even the space between them would only indicate that I've got 2 place values. And how many place values did I really have here? 3. I don't have anything to hold the place between them to separate that there's a missing place value. Okay? All right. So I don't want you to think that this is concerning in the sense that it's going to bother your homework. It's not. It's not going to come up. It's not going to be a problem. You write down this number that looks like 17. This is perfectly legitimate answer. We're all hunky-dory, fine, no problem. Okay? There is no problem here. But there is a logistical real problem for the Babylonians with the system. Do you understand that? And there is a reason we don't use Babylonian today. And this would be one of those reasons. Okay? So, but again, you know, like, are there things that we could fix to make the system workable? Sure. If we had a symbol for the number 0, that would fix a lot, wouldn't it? But you're going to see very quickly another system that has a number 0 that also has problems. And that's the Mayans. Okay, the Mayans have 3 symbols, and I can write all of them, which means you can too. How exciting, right? All right. So the first symbol that they have is they have a symbol for the number 0. And it is the most difficult symbol to write, and it's not difficult. So they write it looks like this. Something like that. It's called a shell. Okay, so imagine like a clam shell. Some of the books I have make it look a little bit different than this. They'll draw it something like this. That wasn't good. They won't do that. Looks kind of like a clamshell. Can you put your imagination to effect there? It does kind of look like a boat. I think it kind of looks like a sandwich too, like a hamburger with lettuce sticking out the side.
Like a really squishy base.
Yes, or even potentially like a football if you didn't have those lines in there in a funny way. All right, so this is our hardest symbol. You ready for the other 2? Symbol number 2 is a dot. That's the symbol. I'm sorry. I wrote the symbol in the wrong spot. The symbol is 1. The value is 1. The symbol is the dot. We'll get them in the right spots. The next one is a value for the value 5. And it's a line, a horizontal line.
That's it, Bubba. That's all 10.
Well, there isn't a 10, but that's not a problem. So we're going to do some repeating of symbols, kind of like the other systems did. So if we wanted the number 10, what would we do? 2 lines. So we can still get a 10. That's not a problem. They do write things vertically. Remember the Chinese? They did that. This says they have a modified base 20 system. So we're going to talk about what the modified part of it means. We're going to talk a little bit about why it's a base 20 and why they modified it as opposed to just being a base 20. We'll do that in a second. And then, just like I had mentioned just a second ago, the 10 is not a problem because we can repeat symbols within the position just like the Babylonians did. So if we wanted 10 $60 bills, well, we just, I'm sorry, not 10's not a good example. 20 $60 bills, we just used two symbols that were both 10s, right? We're going to double up on symbols here. So if we want the number 15, we just use 3 bars. If we want the number 6, we can use 1 bar and 1 dot to get 6. Okay, so before we go on and actually convert anything, I want to talk a little bit about their system. So we know we have a base 10 system. Why do we have a base 10 number system? We actually have 10 symbols if you start with 0. But that's just by default. The symbols came after the fact that we wanted 10 of them. Why would we potentially want a base 10 system? There you go, Terry. It's your hands. You can count to 10 really quick, right? 10 on your hands. And so then if you have the kind of sense of humor that my brother does, you send me emails every now and then. I talk about, teaching on Facebook or whatever, and he'll tell me something like, you should never let your students come to class with shoes on. Because if they have shoes on, Carrie's got her shoes off today, or you've got sandals, right? Then you could actually count to 20. And if you were a Mayan, that would be reasonable because they have base 20. They didn't wear shoes, right? We go shoeless or in sandals, you could see your toes. So base 20, this is what's the deal, okay? Base 20, okay? All right, so here's the next thing. It's not just base 20, it's a modified base 20 system. And it's written vertically like the Chinese, so that the smallest values on top, smallest values on bottom, biggest values on top. Follow my hands, not my words. Okay. So the ones place, we have the 20s place. And then if it were really truly a base 20 system, the next number would be what? 400, 20 squared, right? We do powers of 20. But it's modified. It is not a 20 next. Let me scoot it over a little. The next thing we do is instead of doing 20 times 20, we're going to actually do 20 times 18. And then after that, we're going to do powers of 20. So 20 squared times 18, 20 cubed times 18, and then so forth. Okay, so the powers of 20 are coming into play, but they come into play after this sort of weird 18 is in there. So grab your calculator in your head. What is 20 times 18? 360. What does 360 mean to you?
That's the degrees of a circle.
Degrees of a circle is one issue. So the Mayans had some geometry things that they were working with. They were talking about degrees. There's something else about the 360. It's almost something else. It's almost the number of days in the year. And in fact, in the Mayan calendar, there were 360, not 365 and a quarter days in a year. Okay? So, I don't know about you, but I'm thinking the world did not end last year. I mean, it's still coming, right? 360, that's where the 360 is coming from. It has to do with their idea of the universe being this, this rotating around, all the stuff with 360. The ideas of the circles, the ideas of the days of the year, 360. That's why the 20 times 18 is in there. Okay? So, we understand, and let's just jot these down so that we know. This is the ones, this is 20. We said this is 360. Because we're going to need it in a little bit. Anyway, what's 20 squared times 18? Thank you, 7,200. How about 20 cubed times 18? 144,000. That starts to sound biblical as well. How about 20 to the 4th times 18? We will never need to go higher than this.
288 or 2,888,000.
Awesome. All right, so we're not going to go past 2 million with any of the numbers we're dealing with, but we could continue this process. Agreed? We just do powers of 20 and we can make this work. All right, so let's actually take their number systems first and turn them into ours. All right, just like with the Babylonians, you've got this smaller, larger business going on. Dots are worth less than lines, right? Lines are worth 5, dots are worth 1. They will always have the dots on top of the lines. So if you ever see a line turn into a dot, you've changed place value. So we see one place value change for sure, right? Here. Agreed? Dots, lines, no big deal. We'll have a line and then a dot, change the place value. All right, above the yellow line. I feel like I'm on Biggest Loser, the yellow line. Above the yellow line, what number is above that yellow line? 9, right. What number is below the yellow line? 14. Okay, does everybody see where the 9 and the 14 are coming from? Okay. But what place value is below the yellow line? It's the ones place. What place value would be 1 up from that? The 20s place. Okay, process is the same as it was in the Babylonians. How do I turn from Babylonian into our system? How do I turn from Mayan into our system? What operation? Multiplication. Again, so this actually works a little bit better with our money than it did than the last one did. This is like having only $20 bills and $1 bills right now, right? I have 9 $20 bills, and I have 14 $1 bills. How much money do I have? So we would do the 9 times the 20 plus the 14 times the 1, and what would we end up with?
194.
194. Any questions on that? Fabulous. All right, so on the next one, you see an actual really good rendition of the shell, right? Actually took time to draw it well. All right, so we see the shell. The shell represents 0. It takes up a whole place value system, just like it does in our system. When you see a number 0 there, it means there's 0 tens, or it means there's 0 20. I'm still not using the right number. 0 thousands, right? It means there's 0 of that place value. So it's a place value in and of itself, which means you know for sure there's a line above it and a line below it. It takes up a space. There's 0 of them. All right, so let's look above it and see if there's any other yellow lines. I have 2 dots and then 3 lines. Is that okay? Yeah, that's fine. So we're not going to draw any yellow lines through there. I've got my shell, and then I've got a line, and then a dot, and then another line. I need another yellow line between them, don't I? So here's my line, and I can't do line dot. So there needs to be a yellow line drawn, a place value change between this line and this dot, right here. Okay, everybody good with that? Okay, the first kicker is you got to be able to separate the place values. Because if you can't separate the place values, everything's going to go awry after that. So we're going to have a mess. Second thing to do is what? How much is in each place value? All right, so above the first yellow line, at the very top, what number is that? 17. And then what?
0.
A 0. And then what? And then what?
6.
A 6. All right. Cannot tell you how many times I get tests that will tell me that this answer is 17,056. Okay, every semester it happens. What do we need to do next if we're going to do it correctly? Multiply with our base 20s, right? All stuff with modified base 20s. The place value. So this place value at the bottom is a ones place. What's next? 20s place. What's next? Not quite. 20 times 18 first. Yeah, so this is the 3600s place. But then it's the one that you wanted, Brittany. So it's the 20 squared times 300, or times 20 squared times 18 after that, which is what? 72,000, right. Okay, are we good? Those are the place values that each of those numbers are in, and then I'm going to multiply. So I'm going to take 17 times 7,200, 72,000, sorry, no. Is it 7,200 or 72,000?
72,000.
It's 100. Thank you. I'm sorry.
And it's only 360. Wait a minute.
Okay. I got my numbers all wrong. We fix them, no problem. Thank you. Once I got one wrong, I was definitely going to get the next one wrong because I multiplied by 20. All right. Better? Yeah. All right, how about 17 times the 7,200? Okay, I'm going to write them all out first, but then we'll multiply. And the next one was, it's technically 0 times 360. I'll write it in, recognizing, of course, that that's nothing. And then 5 times 20, and 6 times 1. Does that all look good? Okay. All together, what is this? Are we good? It's almost like you're doing codes, right? Do you remember back when you were a kid and you deciphered codes to try and figure out like the special saying on a puzzle or something like that? This is like this is. I like this because I kind of like puzzles. Okay, you don't have to like it. I'm okay if you don't. But it's kind of like a puzzle. Think of it that way. Okay, we're going to do 2 more. Are they moving past Garrett?
Yeah, it's just a street painting.
Okay, that's what I thought. All right, 208. I'll try to be loud. 208. We got to think about our place value numbers. We want, which I did back on the previous screen. You should still have yours there in yellow here. What is the biggest of these place values that will go into 208? 20, right? 20 is the biggest. So as I'm doing my division, and it is division, right? Everybody remember that. Our number system into theirs is always division. We're going to divide, first off, by 20, because that's the biggest thing that is our place value that will go into this. So how many times will 20 go into 208? 10. You should be able to see that one pretty quick. 10 times 20, again, really fast. 200. And subtracting, I have 8. And I will divide by 1. How many times is 1 going to 8? 8. So this is actually even nicer in this place value, the way it's written, because it looks like it's already vertical, doesn't it? I see a 10, and I'm going to write it on top of the 8 that's going to be written underneath it. That's actually really friendly. So how do I write a 10? 2 lines. How do I write an 8? 3 dots in a line. You guys got the hang of this. Look good? Sounds pretty good. Ready to try another one? The last one, in fact. 58,532. All right, what's the biggest place value that this one could be divided by? 7,200 will work. So this one's division is going to have more in it than the last one did. Quite a bit, actually. All right. So how many times will 58,532 go into 7,200? I said the wrong way, but you know what I mean. Divide. 8. Thank you. What is 8 times 7,200? All right, and then we subtract. So 58,532 minus 57,600. What do I get? 932. I go to the next place value. What's the next place value down from 7,200? 360. All right, how many times will 360 go into 932? Twice. What's 2 times 360? 720. What is 932 minus 720? 212. Okay, what am I going to divide by next? 20. How many times will 20 go into 212? 10 times 20? 200. Subtract. 12. Divide by 1. 12, and I'm done, right? Okay, we always get all the way down to the divide by 1 business, and of course the last answer is the number itself. All right, how do I write an 8? 3 dots and a line. How do I write a 2? 2 dots. How do I write a 10? How do I write a 12? Okay, this is correct. You do this on the test, you do this whatever, and you're done and you're right and it's fine. Now, put on your hat as though you were really a Mayan and tell me what the problem is. Say that loud for me, Lostin.
It thinks it's a 12.
It looks like there's only 3 numbers there, right? It looks like I have an 8 and a 12 and a 12. Again, a problem, right? This isn't good. There's a reason we don't use Mayan anymore, or we don't use it at all, okay? So, again, a flaw in the system. Again, not something to worry about for your...
That's what messed me up.
Thank you, Leah. It's not something to worry about in your homework. It's not going to give you a wrong answer. You're not going to get anything. I mean, none of that's going to happen. I just want you to realize that there are flaws in these systems, okay? All right.